In this video, we're going to go over some practice problems from chapter 6 of our textbook, starting with section 6.3 here. We're going to look at simplifying complex fractions. Now, complex fractions are fractions that have a fraction in the numerator and in the denominator, just like we see with these two examples here. Now, there are two different methods that we'll use to simplify these complex fractions. The first is we're going to take the fraction in our numerator and multiply by the reciprocal of the fraction in our denominator. Then what we want to do is simplify and make sure our final answer is in lowest terms. On the other hand, the second method involves multiplying the fraction in our numerator and in our denominator by the least common denominator of all of the denominators in our complex fraction. Now, again, once we do that, we would simplify and make sure our final answer is in lowest terms. Now, in both of these examples, I'm going to use both methods. What I mean is for this first example, I'm going to use the first method, and for the second, I'm going to use the second method. Now, the reason why I'm going to use the first method in this case is because notice I have a single fraction in my numerator and my denominator. This means that I can easily use the first method because I don't have to simplify the numerator and the denominator separately first. On the other hand, we look at this example, notice I have two different fractions in my numerator and denominator. So this is not a single fraction and this is not a single fraction. If I wanted to use the first method, if I wanted to multiply by the reciprocal of this guy, I would have to first make sure that my fractions in the numerator and the denominator are single fractions. I would have to get a common denominator between these two, subtract and subtract, do some simplification, and then I can multiply by the reciprocal. In this case, if I just multiply by the LCD right away, we don't have to simplify the numerator and denominator separately. Now, before I get started, just wanted to emphasize that I could use both methods on either one of these problems, but one method is more appropriate depending on the formatting of our complex fraction. So let's get started with this first one here. Like I said, I'm going to use the first method. So what I'm going to do is I'm going to take the fraction in our numerator and multiply by the reciprocal of the fraction in our denominator. So that's going to be 6y squared over 2x minus y. So that's our first step. Now, this becomes a multiplication of two rational expressions, and we've seen this before. What we want to do is make sure that each of these guys are fully factored and see if we can cancel anything before we multiply straight across. Notice this first numerator here is not fully factored. 20 and 10 both, or 20x and 10y both share a factor of 10. So what I'm going to do is pull that out. I'm going to be left with 2x minus y. And then my denominator is fully factored, and so is my numerator and denominator of this second fraction. But notice I now have a 2x minus y in the top here and the bottom. So these guys are actually going to cancel, and I'm just going to be left with 10 times 6y squared in the numerator. So we're going to get 10 times 6y squared in the numerator. And then in the denominator here, I'm going to have 12y times just 1. So I'm going to end up with 12y. All right, now we can make sure our final answer is in lowest terms by canceling out any common factors that we have in the numerator and the denominator. Notice in our numerator here, I have two factors of y, and the denominator, I have one factor of y. So these guys can cancel. I'm just going to be left with one factor of y in the numerator. Then if I multiply this 10 and this 6 here, I'm going to get 60. And like I said, I still have that factor of y in the numerator over 12. And then lastly, again, we want to make sure this is in lowest terms, and we know 60 divided by 12 is 5. So our final answer for this one is going to be 5y. So this is how we would simplify this complex fraction using our first method to do so. For the second problem, like I mentioned before, I'm going to use the second method. Now, this method includes multiplying by the LCD of all of the denominators for each of the fractions. So, looking at this first fraction here, the denominator of this guy would just be 1, so we're not concerned with this. Notice the denominator of this guy is 4, this one is also 4, and this one is 2p. Now remember, the LCD is going to be the product of all of the different factors for each of our denominators, and each factor needs to be raised to the highest power. So as we can see, our LCD is definitely going to have a factor of p. This is one of the factors of this denominator, and these guys don't have a p here, so we know the LCD needs to contain at least one p. Now, looking at the other denominators here, this one has two factors. 4 can be split up into two factors, 2 and 2, and similarly for this one. So that means we're going to have at least one factor of 2, but remember, our LCD is going to be the product of all of our different factors raised to the highest power. So although this one has a factor of 2, there's only one 2 here. These guys each have two factors of 2, so that means we have to take both of them. So the LCD in this case would be 2 squared times p, or 4p. So what we need to do then is we need to multiply the numerator and the denominator of this complex fraction by our LCD. And let me actually move this so we have some space to do that. So I'm going to multiply the numerator and the denominator by 4p. Okay. If we don't multiply both of these guys, we're going to actually change this expression. But if we do whatever we do to the top, we also do to the bottom, we're not actually changing this expression. We're just changing how it looks. Okay, so now this 4p is going to multiply this and this. So go ahead and write that out. And on the bottom, this 4p is going to multiply this one and this one as well. So let's figure out what we get in the numerator. 4p is going to multiply this p. So this is going to give me 4p squared. Then 4p is going to multiply this whole thing. And in this case, I'm not going to distribute yet. I'm just going to write this as 4p times p plus 2. And we'll see why in a moment. Now we still have this 4 in our denominator. So that's our new numerator of our complex fraction. Now in the denominator of our complex fraction, I'm going to do the same thing. I'm going to have 4p times 3 in the numerator. So this would be 12p, and I still have that 4 in the denominator. Similarly, for this last one, I'm going to get 20p over 2p. Okay? So this is my new numerator and denominator of my complex fraction after multiplying by the LCD. Now, the whole point of multiplying by the LCD is to make sure that we can clear all of the fractions. Now, if we're unable to clear the fractions after multiplying by the LCD, that kind of tells you that something might have gone wrong. So we multiplied all of these guys by the LCD, so all of these fractions here should be eliminated. And let's go ahead and check that. Notice for this first one here, we have a 4 in the numerator and the denominator. So we can cancel these guys. Similarly here, we have 12p divided by 4. Well, 12 divided by 4 is 3. Then we have 20p in the numerator and 2p in the denominator. Again, these p's can cancel, and we know 20 divided by 2 is 10. So in this one step of multiplying by the LCD, we got rid of these fractions. So we'll go ahead and write that out in our next line here. 4p squared is going to stay as is, but this guy is going to turn into p times p plus 2. That's all that's left over when we cancel out those fractions. Right. Now then in our denominator, we have 12p divided by 4. That's going to give us a 3p. And then again, these p's cancel, so I'm just going to have 20 divided by 2, which is going to give me 10. So again, in that one step, we got rid of these fractions in our numerator and denominator of this complex fraction. Now we want to make sure our final answer is fully simplified and written in lowest terms. So let's go ahead and do that. We're going to distribute this negative p to both terms in our parentheses here to see if we can combine like terms or cancel or factor anything. We're going to get minus p squared minus 2p over 3p minus 10. Now we can't combine like terms here. We have a 4p squared and a minus p squared. So this is going to give me 3p squared minus 2p over 3p minus 10. Now this is actually going to be our final answer. We can't factor anything any further. We can't pull anything out of these guys. We could pull a p out. These do share a common factor of p, but pulling that out isn't going to allow us to cancel with anything in the denominator. So this is as far as we're going to go. This would be our final answer when we simplified our original complex fraction. Now, in this next example, we're again wanting to simplify a rational expression. But notice that each of the terms in my numerator and denominator of this fraction here have negative exponents. So the first thing that we need to do is rewrite these guys with positive exponents. Let's go ahead and do that. X to the negative second power, written with positive exponents, is going to be 1 over x squared. Similarly, with this y here, we're going to get 1 over y squared. So that is our new numerator. This whole thing turned into this. Let's do the same thing for our denominator. We're going to have 1 over x plus 1 over y. So by rewriting these guys with positive exponents, we turned this rational expression here into a complex fraction. So we need to go ahead and simplify it. Now, again, like I mentioned, there are two different methods, but if I do not have a singular fraction here for my numerator and my denominator, I'm not going to use method one. If I wanted to, I would first have to get a common denominator, add these guys together, and it creates some extra steps. Instead, since I have two separate fractions in my numerator and denominator, what I'm going to do is multiply by the LCD. So that's the first thing that we need to do. We need to find the LCD. Now, this is going to be the product of all of our different denominators raised to its greatest power. So all of our denominators share at least one factor of y, but again, it needs to be that factor raised to the greatest power. So our LCD in this case is going to be x squared y squared. Now, like I said in the last example, the whole point of multiplying by the LCD is to get rid of these fractions. If we were to take that the LCD was just x times y for this example, when we went ahead and multiplied the top and bottom by this LCD, if it were x times y, we would see that these guys wouldn't cancel out. So that would kind of give you an idea that maybe we made a mistake with this selection. So keep that in mind when you are checking your work, but we're going to go ahead and multiply both sides by this LCD, or not both sides, the top and bottom of this complex fraction. All right, so when we multiply by the LCD, let's see what we get. Again, this LCD is going to be multiplying both of the fractions in our numerator and denominator. So for this first one, we're going to get 1 times this LCD. So we're just going to get x squared y squared over our denominator x squared. For the second one, we also have a 1 in the numerator, so we're going to get x squared y squared over 1 squared. Then in our denominator of our complex fraction, we're going to get x squared y squared over x plus x squared y squared over y. All right. Now, again, like I said, multiplying by the LCD should cancel out our fraction. So let's make sure we go ahead and do that. We're going to have an x squared on the top and bottom of this first fraction, a y squared on the top and bottom. Now, for this denominator here, we have two factors of x in the top and one on the bottom. So we'll take one of those out. And similarly for our y factors. So after everything's canceled, let's see what we have left. We're going to be left with just a y squared plus an x squared in our numerator. Then in our denominator here, we're going to be left with one factor of x, and we're still going to have this y squared. So we're going to have x y squared. And then in our last fraction here, we're going to take out one of these factors of y. So we're going to be left with x squared y. All right, now from here, it looks like this is also going to be our final answer. We can't factor anything out from this guy. We could factor out an x times y from our denominator. Um, so for example, that would look like this here. We're going to take out an xy from both terms. So if I take out an xy from this, I'm just going to be left with a y. And if I take out an xy from this, I'm just going to be left with an x. So even by factoring out our common factor for both of these terms, we still see that we can't cancel anything out. So our final answer could be either one of these. Yep. So that's how we would simplify a complex fraction if we started out with negative exponents. This brings us to section 6.4. Now in this section, we're going to be actually solving rational equations and graphing them. But before we can do that, we need to make sure that we can find the domain of a rational equation. So, for example, we want to find the domain of this equation for our variable x. Now, if you remember, with rational equations, the domain of these guys are going to be all real numbers except those numbers that'll make our denominators equal to 0. Because remember, we can't divide by 0. So again, our domain is going to be assumed to be all real numbers except those x values that'll make our denominators equal to 0. So in order to find those values that we're going to exclude from our domain, what we're going to do is set our denominators equal to 0 and solve for the variable. So let's set this denominator equal to 0. We have x minus 4 is equal to 0. Well, if x minus 4 is equal to 0, then this must mean x is equal to 4. We can find this by adding 4 to both sides of this equation. So we're going to get that x is equal to 4. So this is the value that we're going to exclude from our domain, because if x is equal to 4, then this denominator gives us 0. And again, we can't divide by 0. So that's one value that we need to exclude from our domain. The other value comes from our second denominator. We have to check both of these. So we're going to set our second denominator equal to 0 and solve for our variable x. The first thing I'm going to do is add 7 on both sides of my equation. I'm going to get 2x is equal to 7, and then lastly divide by 2 to solve for our variable x. So x is going to be 7 over 2, or 3.5. So this is the other value that we're going to exclude from our domain. If we were to plug 7 over 2 into this x here, we would get 0 in our denominator. So our domain is going to be all real numbers except for 4 and 7 over 2. So we'll write that here. Our domain is going to be all real numbers except 4 and positive 7 over 2. And then in interval notation, we would say negative infinity up to our smallest value that we're going to exclude. So that would be this one, up to 7 over 2. And then we're going to have a parenthesis enclosing this interval to indicate that we're not actually taking this value. Then we're going to take 7 over 2 up to 4 because everything in between these two values that are going to be excluded can still be a part of our domain. And then lastly, 4 all the way up to infinity. And again, these parentheses here indicating that we're not actually taking these values. All right, so that would be the domain for this. Now, the whole reason we are finding the domain for our rational equations before we solve them is because whatever solutions that we get when we solve these rational equations are just proposed solutions. We need to make sure they're actually solutions by making sure that one, they're actually in the domain that we find, and two, they satisfy the equation if we were to plug them back into our original equation. Now for this example here, it doesn't ask us to solve, it just asks us to find the domain. So that's it for this question. But with that being said, let's look at the next two examples. So again, like I said, what we want to do is solve these guys. And whatever solution we get, we need to make sure that they're actually in our domain. So the first thing that we need to do is find the domain for our rational equation. So looking at this one here, we want to figure out which values of x are going to make any of these denominators equal to 0. So notice, looking at this first fraction, our denominator is 4x. The only value of x that'll make this guy 0 is 0. Similarly, for this one, the only value of x that'll make this 0 is 0. And lastly, this denominator will never be equal to 0 because we just have a 4 here. We don't have any variable quantity. So our domain is going to be all real numbers except for 0. So I'm just going to write this in shorthand here. X can be anything except for 0. So with that in mind, what we want to do is solve this. And if we were to get that 0 is our answer, we would say that this doesn't have a solution because that's not part of our domain. So let's go ahead and solve this rational equation here. Now, in order to solve rational equations, what we need to do is multiply both sides of our equation by the LCD. The whole idea is to, again, get rid of our fractions. So looking at this here, our LCD would be 4x. This is very similar to one of the first examples we saw in this video in section 6.3. In that case, our LCD was 4p, and we have the same kind of setup here. We have this is a 4, this is a 2x, and this is a 4x. We need to take the LCD is going to be the product of all of the different factors of each of our denominators raised to the highest power. So each of these is going to have a factor of 2, but raised to the highest power would be 4. Then both of these has a factor of x, so we also need to include that in our LCD. So our LCD then is going to be 4x. So once we find that, we're going to multiply both sides of our equation by that LCD. So in this next line here, we're going to have 4x times 3 over 4x on the left-hand side of our equation. On the right-hand side, we're going to have 20x divided by 2x minus 28x over 4. Now, again, the whole point of multiplying by the LCD is to cancel out our fractions, and so let's make sure we get that. On the left-hand side, we have a 4x in the numerator and the denominator, so these guys are going to cancel. On the right-hand side, we have 20x divided by 2x. So we have an x on the top and the bottom, those are going to cancel. And then we know 20 divided by 2 is 10. So we got rid of this fraction as well. Similarly, 28 divided by 4 gives us 7. So we can reduce this as well. Our new equation is just going to become 3 by itself on the left-hand side. On the right-hand side, we're going to have 10 and then minus a 7x. So just by multiplying by the LCD, we took this complicated rational equation and turned it into an equation that we're definitely more comfortable with solving. So we need to solve for this variable x. So what we're going to do is, let's subtract 10 on both sides of our equation. Doing that, we're going to get negative 7 is equal to negative 7x. So lastly, we're going to divide both sides by negative 7. We're going to get that x is equal to 1. Now, once we get this solution, like I said before, this is a proposed solution. So one, we need to make sure that it's in our domain. And again, our domain is going to be all real numbers except for 0. So that means this is in our domain. But we also want to check to make sure that this solution is in fact a solution by plugging it into our original equation and making sure that we end up with a true statement. So if we were to plug in 1 to this x, we would get 3 over 4. Plugging 1 into this x, we would get 3 over 4 is equal to 5 over 2 minus 7 over 4. We would get a common denominator here and subtract them, and we would in fact get 3 over 4. So this is going to be a solution to our original equation. And so our final answer is going to look like this. Our solution set consists of x is equal to 1. So that would be our final answer. Now for this next example, we're going to do something similar. We again want to solve this. So what we're going to do is multiply both sides of our equation by the LCD. But first we want to make sure that we can identify what the domain of this equation is. And before we even do that, we want to make sure that everything in our denominators are fully factored. Because remember, our LCD is going to be the product of all of the different factors of our denominators. So if our denominators aren't in fully factored form, it might not be as easy to see what these factors are. In particular, looking at the fraction on the right-hand side of our equation, this guy, this x squared minus 4x, this is not in fully factored form. So before I do anything, I'm going to rewrite my equation to make sure that all of my denominators are fully factored. Now this guy is going to be, actually at first it might look like a difference of two squares, but it's not quite because we have this x here. But we still can factor this because they share a common factor of x. So I'm going to pull that out from both of my terms. I'm going to have an x on the outside, and I'm going to be left with x minus 4. All right, so that'll be step one to make sure that all of our denominators are factored so we can easily see what the LCD is. So remember, the LCD is going to be the product of all of the different factors. Well, one factor of one of our denominators is this. The other factor is this x here. And then our last denominator has both of these factors in it. So our LCD is going to be exactly that. It's going to be x times x minus 4. All right, and then like I said, we also want to make sure we identify the domain. So the domain is again going to be all real numbers except those that'll make our denominators equal to 0. So looking at this first denominator, this was going to be equal to 0 if x is equal to positive 4. If I were to plug positive 4 into this, I would get 0 in my denominator. So my domain is going to be all real numbers except for negative 4, sorry, positive 4. And looking at our second fraction here, if x is equal to 0, this denominator is going to be equal to 0. So that's going to be another restriction. X cannot be equal to 0. And let's look at our last denominator here. This is going to be our LCD. And we're actually going to have the same restrictions on our domain here because if x is equal to 0, that'll make this whole thing equal to 0 because 0 times anything is 0. Similarly, if we plugged in 4 here, that would make this guy 0, and anything times 0 is 0. So our domain is just going to be all real numbers except for 4 and 0. So once we've done those two steps, I guess 3 steps, factoring, finding the domain in LCD, we can now multiply both sides by the LCD. So let's go ahead and do that. I'm going to multiply both sides of the equation by the LCD. All right. Doing so, let's see what we get on the left-hand side of my equation. So in my numerator, my first fraction, I'm going to get 6x times x minus 4 over x minus 4. We're already starting to see that some things will cancel. And then on the right-hand side of my fraction, or my equation, I'm actually going to cancel right away. We know that we're going to get negative 20 times this over this. So by multiplying by the LCD, my fraction on my right-hand side disappears. I'm just going to have negative 20 on the right-hand side of my equation. All right, so from here, let's cancel some things. Looking at my first fraction, we have an x minus 4 on the top and bottom. Those can cancel. Then my second one, I have a 5 or an x on the top and bottom. Those can cancel. So I'm just going to be left with 6x plus 5 times x minus 4 is equal to negative 20. Now again, we want to solve for our variable x. So let's go ahead and do that. We're going to expand this equation and see if we can simplify by combining like terms. So here I have a 6x and a 5x, so I can combine those, and I also have this minus 20 here, so I'm going to add it to this side of my equation. So adding 20 to both sides of my equation, I'm going to end up with 11x is equal to 40. And sorry, That is close here, but notice that I dropped a negative from this guy. So I'm actually going to get a negative 20 here. Okay, so in the same step, again, I'm going to combine these like terms, but I'm going to move this 20 over here by adding 20 on both sides. When I add 20 on both sides, these are going to cancel, but so are these guys. So I'm going to end up with 11x is actually equal to 0. All right, now again, I want to completely isolate x, so I'm going to divide both sides by 11, and I'm still going to get that x is equal to 0. So this is going to be my proposed solution. What I need to do is first make sure that it's in the domain, and two, plug it into the original equation to make sure I get a true statement. So going back up to our domain, notice our domain is going to be all real numbers except for 4 and 0, but we got that 0 is our proposed solution. So since this isn't in our domain, it's not going to be a solution. So I'm going to say not in our domain. So this is an example of a rational equation that has no solution. The only solution that we got is 0, and that's not in our domain. So our final answer in this case is going to be that the solution set is the empty set. We have no solution for this example. Now, in the end of section 6.4, our last objective deals with graphing rational functions. So we're going to do so using this information here. Now, this is a screenshot taken directly from our textbook in section 6.4, objective 3. What we're going to do is we're going to focus on this rational function here. This is the reciprocal function. So f of x is equal to 1 over x, and it's the reciprocal function because whatever values we plug in for x, our output is always going to be the reciprocal of that. Okay, so this is essentially kind of our parent function for the rational functions that we're going to graph. So here is a table of some input and output values for this function. Like I said, it's the reciprocal function. So if I were to plug in, for example, -3 into x, my output is going to be the reciprocal of that, -1/3. If I were to plug in 2, our output is going to be the reciprocal of that, 1 over 2, and so on. Now, in this case, our domain is going to be all the numbers except for 0, because if we were to plug in 0 into this function, our output would be undefined because we can never divide by 0. So our domain is going to be all real numbers except for 0. Now, something to notice here is that the closer the negative values of x are to 0, the less or more negative y is. So what we're saying is, if we get closer and closer to 0 here, these are small negative values, the bigger our output for y is. On the other hand, the closer positive values of x are to 0, the greater y is. So for example, if we have a really small value for x, this 0.1 here, our output is going to be really big. Right? If we divide by a really small number, our output's going to be really big. And on the other hand, if we increase these values in either the positive or negative direction, these values get really, really small. So that's kind of the behavior of this function. And we can see this in our graph as well. This is going to be the graph of our reciprocal function. So what we can do is we can take some of these nicer points, like -3, -1, 1, 2, and 3, and plot them on this graph here to kind of see the behavior of this function. But like we said, if we increase our x values in the positive direction, for example, our outputs are going to be really small. So for example, if I were to increase my input values over here, so I'm going to get bigger and bigger in this direction, my outputs are going to be really, really small, but they're never actually going to be 0. So what's going to happen is that this curve is going to get really, really close to this x-axis here, but it's never going to touch this x-axis because my output can never be 0. Similarly, we can't input 0 into this function. So this brings up two kind of invisible lines here on our coordinate plane called asymptotes. So these are, like I said, invisible lines that our graph cannot pass. So we're going to have a vertical asymptote here at x is equal to 0 because this is not part of our domain. So our graph cannot touch this. Our graph will never have this input value, x is equal to 0. So this is our vertical asymptote. So our vertical asymptote, again, comes from our domain. Then our horizontal asymptote comes from the fact that our output is never going to be 0 either. As we increase our x values in either direction here, this graph is going to get really, really close to 0 here and really, really close to 0 here, but it's not actually ever going to give us an output value of 0. So this is the behavior of our reciprocal function, and we're going to use this to graph other rational functions. All right, so this brings us to these two examples. We want to graph both of these rational functions. Now let's start with this one here. Now this one looks very similar to the one that we just talked about. Notice we have an x in our denominator for our reciprocal function here and an x in this denominator. So they're going to have the same domain. Our domain is going to be all real numbers except for 0, because plugging in 0 for this x would make this guy undefined. So this tells me we are going to have a vertical asymptote here at the line x is equal to 0, and we'll indicate that with this dashed line here. So we're going to have a vertical asymptote there. Now we also want to figure out what our horizontal asymptote might be, and it's going to be kind of similar to what we see here. Remember, as we increase our x values, so as x gets bigger in the positive direction or in the negative direction, our y value gets really, really small. So this means as our x values get large, our graph is going to approach the x-axis, but not actually cross it. So we're going to see the same behavior here. As we increase our x values, as these get very big, this output is going to get really small. So the bigger our x values are in either positive or negative direction, the closer our graph is going to be to this x-axis, but it's not actually going to cross it. So we're going to have a horizontal asymptote at this point, or at this at the x-axis, at the line y is equal to 0. So now we kind of identified the behavior of this function. It's very similar to the reciprocal function, except we have this 2 here. And notice we also have this negative here. So this tells me that my outputs are going to have the opposite signs as what we see for the reciprocal function. Going back to the reciprocal function, our outputs were only negative if our inputs were negative, and our outputs were positive if our inputs were positive. On this hand, if I were to input a positive value in this x here, my output's going to be negative. So for example, let's look at nice numbers. If I were to input 1 into this function here, my output would be -2. So this tells me that all of my values are essentially going to be flipped about the y-axis here. The graph is going to look like this. It's going to be similar because we have the same domain and behavior as our reciprocal function, but all of these outputs are going to be in the opposite quadrant, because if I input a positive, I'm going to get a negative, and if I input a negative into this function, I'm going to output a positive value. So everything's going to be flipped about this y-axis. So in order to kind of show this, let's look at some points. Let's plug in some points into this function. We're going to plug in some x values and see what's outputted. And we'll pick some nice numbers. For example, let's pick 1. If we plug in 1 into this function, my output's going to be -2. So that'll be our first point. If I plug in 1, my output's going to be -2. So we'll have that point there. Let's see what happens if we plug in a -1. If I were to plug -1 into this, I'm going to get -2 divided by -1, which gives me a +2. So -1 gives me a +2. All right, let's keep going with some nice values. I'm going to plug in a +2 here. My output would be -1. So +2 gives me a -1. And then on the other hand, if I were to plug in a -2, I would get a +1. So -2 gives me, oh, sorry, -2 gives me a +1. So those are two nice points on this graph here. Now we know the behavior of this graph. We know that it's going to behave similar to this. It's not going to cross these vertical and horizontal asymptotes. As we increase our x values in this direction or this direction, the values are going to get really, really close to our x-axis but not touch them. So if I increase x in this direction, all of my outputs are going to be really close to this x-axis but not touch it. On the other hand, if x is really, really small, then my outputs, my y values, are going to get bigger. So if I were to plug in really small values into this x, my outputs are going to get bigger and bigger in this negative direction here, because we have this negative out front. So my graph is going to behave like this. All of my outputs are going to get really big as I make my x value small and small, or smaller and smaller, but it's not going to cross this vertical asymptote. Similarly for this guy, if I were to plug in a bunch of negative values here, the bigger those negative values get, the smaller my y value is going to get, but it's going to be positive because I have this negative out front. If I were to plug in a negative here, my output would be positive. So we know that as we increase my x values in the negative direction, my graph is going to behave like this. It's going to get really close to the x-axis, but not actually cross it. On the other hand, if I make my x values really small over here in this negative region, my outputs are going to be really, really big, but never crossing this y-axis because we have that asymptote. So that's how we would graph this rational function here. Now, again, we can just plug in points and see what is outputted, but it's a good idea to figure out what our asymptotes are so we can easily see what the behavior of this function is going to look like. Now, this next graph is a little different. Notice we again have somewhat of a reciprocal going on here. This is going to look very similar to our parent function, but in our denominator, we have this plus 2. So this is actually going to change the domain of this function compared to the reciprocal function. Because if I were to plug in 0 for this x, this would not make my output undefined. So we want to figure out what value of our x here is going to make this denominator 0. We know that that value is going to be -2. If I were to plug in -2 into this x, I would get 0 in my denominator. So the domain for this one is going to be all real numbers except for -2. So I can't plug in -2 into this input. Well, that's going to change our vertical asymptote. Remember, our vertical asymptote is going to be the value excluded from our domain because x can never be equal to that value. So for this one, our domain was that x is going to be all real numbers except for 0. So we're going to have a vertical asymptote at this point because we're never going to hit x is equal to 0. Now in this case, we're never going to hit x is equal to -2. So this is going to shift our vertical asymptote 2 units to the left at the point x is equal to -2. So since x can never be equal to -2, this is our new vertical asymptote. Now, we're still going to have a horizontal asymptote here for the same reasoning. If we increase our x values in the positive or negative direction, our output is going to get bigger and, or sorry, smaller and smaller. So it's going to get closer and closer to our x-axis. So we're again going to have a horizontal asymptote here at y is equal to 0. Okay, so again, just to emphasize that, if I increase my x values in this direction, my output is going to be really small. So it's going to get really, really close to the x-axis. And similarly in this direction. Now, what we want to do then is plot some points. Essentially, what's happening compared to our parent function is this vertical asymptote is just being moved over 2 units to the left. So we could take these points here and just move them over. But let's put in some values into our function and just see what is outputted. So we'll do the same thing here and we'll pick nice values. Um, First, let's plug in a 0 and see what we get. If I plug in 0 into this function, my output is going to be 1/2. So x is equal to 0, my output is going to be 1/2. So I'm going to go right here. All right. Now, let's say I were to plug in 1. Were to plug in 1 into this function, my output is going to be 1/3. So plugging in 1, my output's going to be 1/3. So something like that. We know if we increase my x values in this direction, my output's going to keep getting smaller and smaller. If I plug in 2, I'm going to get 1/4. If I plug in 6, I'm going to get 1/8. So this is just going to get smaller and smaller, really close to this x-axis, but never actually crossing it. All right. Let's see what we get if we plug in x values in this region here. If I were to plug in -1 into this, my output is just going to be 1. If I plug in -1 here, I'm going to end up with a 1/1. So my output would be 1. So that would be this point. Mm. Now, I can't plug in a -2, but we know that if we get closer and closer to this region, we're not able to cross this asymptote. So that means if I were to pick values around here, maybe -1.5 and so on, or values really, really close to -2, my outputs are going to look like this, never actually crossing that vertical asymptote. So my graph for this one is going to look something like this here, where we're never crossing our vertical or horizontal asymptotes. But we still need to figure out what's going on in this region. What about all of our x values past this excluded point of -2? So let's figure out what happens if we were to plug in -3 into this guy. If I were to plug in -3 into this, I'm going to end up with a -1 in my denominator. So my output would be -1. If I plug in -3, I'm going to get a -1. All right. Let's see what happens if I plug in a -4. Plugging in a -4 here, I'm going to end up with a -2 in my denominator. So my output's going to be -1/2. So it's going to kind of mirror what we just saw on the other side of this asymptote here. We're going to have, sorry, if I plug in a -3, I should get a -1. So -3 gives me -1, so that point should actually be here. Sorry about that. But we're going to have the same behavior. If I plug in -4, my output's going to be -1/2. So -4, I'm going to get a -1/2. If I were to plug in, let's say -5, -6, and so on, these outputs are going to keep getting smaller and smaller. So my line is going to get really close to this x-axis, but not cross it. Similarly, if I were to plug in any points between -3 and -2 here, let's say -2.5, that point's going to be right around here, and any values really close to -2 on this side of my asymptote are going to make our outputs really, really close to this asymptote, but never actually cross it. So my graph here is going to look, is going to look something like this. It's going to get really, really close to these asymptotes, but not actually cross it. Okay. So that's how we would graph these two rational functions. All right, so this brings us to our last section in this video. Now in section 6.5, we're going to be looking at applications of rational equations. Now, before we get into some of those problems, we first want to make sure that we can solve a rational equation for a specified variable. So for example, here we have this rational equation and we want to solve for the variable r. In order to do that, we need to completely isolate r. Now notice we have an r in the numerator and the denominator here. So maybe we're not sure how to go about this at first, but remember with rational equations, we always want to make our lives a little bit easier. And in order to do that, we're going to get rid of our fractions. So in order to get rid of this fraction, what we're going to do is multiply both sides of this equation by this denominator. So we're going to multiply by 1 plus RT on the right-hand side. And whenever we do to one side of the equation, we have to do to the other. Okay, by doing this, we've canceled out the fraction here. So now we're just going to be left with d times 1 plus rt is equal to r. All right, now we have this multiplication here, so maybe let's distribute this d to both terms in our parentheses. So we're going to multiply this and this. We're going to end up with d plus drt is equal to r. Okay, now we're getting somewhere. We don't have any multiplication or division going on. And again, we're trying to isolate this variable r. So let's try to get both of our r terms to one side of our equation. In order to do that, I'm going to subtract drt on both sides. And I have to take this whole thing because drt is one whole term. So I'm going to get d is equal to r minus drt. And again, we're trying to completely isolate r. We have two terms with r's in them, so that means both of these terms share a common factor of r. So I can go ahead and pull that factor out. Pulling out an r from both of these terms, I'm just going to be left with a 1 minus dt. And we can always check our work by redistributing this r and making sure we end up with this guy. Now I have r as being multiplied by this. So if I want to completely isolate it, what I'm going to do is divide by 1 minus dt. Whatever I do to one side of the equation, I have to do to the other. So I'm going to get d over 1 minus dt is equal to r. Now I've completely isolated this variable r here, so this would be my final answer. Okay? So that's how we would solve a rational equation for a specified variable. Now for this next example, we're going to look at an application problem. So we're told that in 2021, the average ratio of teachers to students in public elementary and secondary schools was 1 to 15. So 1 out of 15. If a public school had 870 students, how many teachers would be at the school using this ratio? So we're going to use this ratio and we're going to actually set up a proportion. So first things first, let's figure out what we're trying to find. We're trying to find how many teachers would be at the school using this ratio. So this is going to be our variable x. This is our unknown quantity that we're trying to find. Now we're going to use the previous ratio in order to find this variable x, and we're going to do so by setting up a proportion. We're told in the beginning that the average ratio of teachers to students is going to be 1 to 15, meaning there's one teacher for every single student. Now we're going to set up a proportion. So we're going to set this equal to another ratio. And this is going to be equal to the second ratio that we're given. We're given that if a school had 870 students, how many teachers would be at the school? Using this ratio, our teachers are going to be on the top and our students are going to be on the bottom. So this is what's called a proportion. A proportion is two ratios being equal to each other. Overall, we're told that the average ratio of teachers to students is 1 to 15. Now, if we're using this on average, that means X amount of teachers to 870 students, this ratio must be equal to this one. So this is a proportion, and what we need to do is solve for X. Now, there's a couple different ways that we can do so. We can multiply both sides of our equation by 870, see if it'll take out this 15, see if 15 or 870 is divisible by 15. The simplest way, though, would be to actually cross multiply. What we're going to do is we're going to multiply across our equal sign. So 15 times x and 870 times 1. Doing that, we're going to end up with 15x is equal to 870. All right, so now we turned this proportion or this rational equation into a much simpler one. What we'll do is solve for x by dividing by 15 on both sides of our equation. We're going to end up with x is equal to 870 divided by 15, which is going to be 58. So this means there would be 58 teachers using the given ratio. All right, let's look at our last example. So we're told that in his boat, Leonard can travel 24 miles upstream in the same time that it takes to travel 36 miles downstream. So we're dealing with a distance, rate, and time problem. If the rate of the current is 2 miles per hour, find the rate of the boat still in the water. So this is our unknown quantity that we want to find, the rate of the boat still in the water. So this is going to be our unknown variable x. So this is what we're trying to find. Now, like I said, this is a distance, rate, and time problem. So we're going to use the fact that distance is equal to rate times time. All right, so now let's kind of assign some equations and write down what we know so far. We know that Leonard can travel 24 miles upstream in the same time that it takes to travel 36 miles downstream. So we're going to split this up into upstream and downstream. We're going to have different rates for each of these, taking into account the current. So, upstream, we know that we're going to travel 24 miles. This is going to be our distance. So I'm going to label this as D. And we know downstream, this distance is going to be 36 miles. All right. We don't have our rate for either of these. We just know that the rate of the current is 2 miles per hour. We also aren't given the time. But notice it says that Leonard can travel 24 miles upstream in the same time that it takes to travel 36 miles downstream. So what we're going to do then is we're going to rewrite this equation in terms of time. T is going to be equal to distance over rate. So since it takes the same amount of time to travel upstream and downstream, what we can do is we can create two different equations and set them equal to each other. So that's the idea here. Now, if we're thinking of this in terms of time, so far we have the distance for upstream travel and downstream travel, but we don't have the rate for either of those. So what we need to do is identify the rate in both of these cases. Now, the rate of our travel upstream and downstream is going to depend on the rate of our current. So, for example, if I'm traveling upstream, this means I'm traveling against the current. So, my rate is going to be the rate of the boat minus this current. I'm going to be traveling x minus 2 miles per hour because we're traveling upstream against that current. On the other hand, if I'm traveling downstream, then my rate is going to be the rate of the boat in the water plus this current. Because if I'm traveling downstream, that current is pushing us, it's going with us. So, the rate in this case is going to be x plus 2. So, if I'm thinking of this in terms of time, for my upstream travel, t is going to be equal to the distance over the rate. So this would be 24 over x minus 2. And then downstream, this would be the distance over this rate. So now I have two different equations. And like I said, this is all going to happen in the same amount of time. So that means this time must be equal to this time. So now I can set these two equations equal to each other. I'm going to have 24 divided by x minus 2 is equal to 36 over x plus 2. All right, so now I have a rational equation. Now, there's a couple different things that we can do to solve for this guy. So far, what we've seen is we're going to multiply by the LCD. Now, we can do that, or again, we could cross multiply just like we saw in the last example. So I'm actually going to do the cross multiplication way, but if you do want to multiply by the LCD on both sides of our equation, I'll go ahead and write this out for us. So the LCD is going to be the product of the different factors of each of our denominators. So the LCD is going to be x minus 2 times x plus 2. So what you do is if you multiply by the LCD is multiply both sides of the equation by the LCD. Um, or what you can do is cross multiply. So if I cross multiply, I'm going to take 24 times this, and 36 times x minus 2. I'm going to get 24 times x plus 2 is equal to 36 times x minus 2. Now, this is what we're going to get if we cross multiply. Like I said, if you want to use this method here, you'd multiply both sides by the LCD. And notice if you did that, this x plus 2 would cancel with this one. So you'd end up with 36 times the remaining factor of your LCD. And on this side, this x minus 2 would cancel with this one. So you'd end up with 24 times the remaining factor of your LCD. So that's exactly what we got here by cross multiplying. Now, something to note here is that we can only cross multiply if we have something set up like this. If we had another term on this side or on this side, we wouldn't be able to cross multiply by like this, and we'd have to multiply both sides by the LCD. So just keep that in mind here. But in this case, cross multiplying is easier. We can go ahead and distribute this 24 to both sides of our equation. We're going to get 24x plus 48 on the left-hand side of our equation. Then on the right-hand side of our equation, we're going to distribute that 36 to both terms in our parentheses. And so we're going to get 36 times x here. So this would be 30, and then 36 times 2, and then that's going to give us a negative 72. All right, so from here, we want to solve for our variable x. So we're going to combine like terms. I'm going to move all of my x terms to one side of the equation and all of my constant terms to the other. So I'm going to subtract 24x on both sides of my equation, and I'm going to add 72 on both sides. Okay. On the left-hand side of my equation, I'm going to have just my constant terms. 72 plus 48 gives me 120. Then on the right-hand side, I'm going to have 36x minus 24x. That's going to give me 12x. Lastly, I want to divide both sides of this equation by 12 to get x completely alone. We're going to get that x is equal to 10. So this tells me that the rate of the boat still in the water is going to be 10, and in this case, our units are miles per hour, right? So that is two examples of some application problems using rational equations.